Thank you, Luke, and for giving me this chance to present. And thank you, everybody, for joining today. As Luke said, I will be talking about quantifying, attributing, and understanding time-step sensitivities in the E3SMv1 atmosphere model. And this is some recent work that has been done with my colleagues as part of a SciDAC project. Okay, so the background of this work is that in the past few years, we have been seeing an increasing number of significant and undesirable numerical artifacts in models like E3SM, both in global and regional simulations, and both at traditional lower and also newer, much higher resolutions. And from our own work a few years back, we noticed that if we do a time-step convergence test using the E3SM atmosphere model, we will notice that not only the time-step convergence rate is very low when we turn on all the physics parameterizations, but also the time-stepping error appears to be large, and again, mostly from the physics parameterizations. So my colleagues and I were fortunate to get funded for a SciDAC project that aims at addressing this time-stepping error in physics parameterization research area. In the first first half of that project, we made investigations using mostly simplified models, and we were able to demonstrate that even when parameterizations are turned on, it is still possible to understand why convergence gets lost and how we can get it restored. And also we noticed that during the investigation of convergence issues, we can identify inconsistencies in the model between numerical methods and the intended continuous equations, or sometimes even between the formulated continuous equations and the actually intended physics. And we also saw that when we address the convergence issue by making revisions to the equations or numerical methods, we can cause pretty significant changes in the model climate when you put those changes back into a full-fledged atmospheric model. Starting about a year ago, our project is in its second phase, and now we would like to move away from the simplified models and start to work, really address the issues in the current and future versions of the EAM model. So then naturally we ask ourselves the question, how should we set the priorities so that we can contribute to E3SM more directly or effectively? And also we sense that every now and then our colleagues who focus more on the physics aspects and also on reducing model biases in their day-to-day work might ask, okay, you get things nice and clean under the hood. That sounds cool, but what is the impact on my work? So to address that second question, which is basically a relevance question, we did a pair of pretty straightforward simulations with the E3SM atmosphere v1 model. They both use the F2000 COMSAT and the 1 degree horizontal resolution. So in one simulation, we just ran the model out of the box using all the default parameters, default step sizes. And then in the second simulation, we reduced all the major steps, step sizes to 1/6 of the default value. And then we got a 10-year mean climate. We compared the global average and the geographical distribution of a number of physical quantities by comparing the model results to the observation data that is available from the AMWG diagnostics. And on this slide, you see these these bars showing the biases in these two simulations compared to the observation. And so the upper panel is the biases or errors. Now we normalized them in the global mean values, and then the lower panel is basically the error in global pattern. And cyan is our default model, and then orange is the simulation where we reduce the step sizes. So overall, the general impression is that when we reduce step size, the model biases systematically go up, which is probably not surprising at all, given that we all know our model developers have spent a lot of time carefully tuning the model and trying to optimize the match between simulation and observation. But if I add the V0 simulation to this plot, which is now indicated by these dark green bars, you might realize that the degradation of model fidelity when we shorten the model step size in the V1 model is, in terms of magnitude, pretty close to the improvement that we saw when the model was evolved from V0 to V1, which is not very nice. And so I think basically for us and this group of people who are working on numerical methods and time integration errors, what we conclude from this figure is that our model contains a significant amount of time integration error that is usually maybe compensated by either parameter tuning or by other sources of model error, which in our view is an issue that needs to be addressed. And also the fact that when you change model time step, the model skill score can change significantly is, I guess, a pretty inconvenient fact to our colleagues who work on a daily basis on improving model fidelity. So the key signatures of the time step sensitivity are mostly seen in quantities related to clouds and cloud and moist processes. Here I'm showing zonal mean 10-year averages of relative humidity change on the left and cloud fraction change on the right when we compare the two simulations with different step sizes. And in terms of relative humidity, we see a systematic drying or lowering of relative humidity throughout the troposphere. And for cloud fraction, we see a significant decreases in the subtropical lower troposphere, and also in the upper troposphere pretty much at all latitudes. And in terms of geographical distribution, the most prominent signal we see is a systematic and rather substantial decrease of total cloud cover in the subtropical region, especially over the ocean. And so these changes, these decreases in relative sense are about 20 to 50% of what we have in the default model. And because we know that these clouds have a strong radiative impact, so for example, shown here on the right is the net cloud radiative effect changes when we introduce the time step change. So these sensitivities raise the question whether we need to be concerned about the climate change predictions made by our model. So we published some, we submitted some of those results that we are talking, that I'm talking about today to GMD, and one anonymous reviewer said in his comment that perhaps unsurprisingly to those familiar with model development, the largest deviations, I think he meant sensitivities, can be attributed to the parameterizations of clouds and moist convection. Perhaps less predictable is how and where these deviations are. We certainly fully agree with the reviewer. And in addition to this how and where the sensitivities are question, we think also there is so the next set of questions that we need to ask, which is what components of the model have caused these changes and why? So when asking those questions, and it's useful to mention that the time integration and especially process coupling in the E3SM atmosphere model is pretty sophisticated. It involves multiple levels of subcycling and with different various different physical processes and also the dynamical processes using different step sizes. So that is a complexity, sometimes making us feel a little bit daunted, but also this provides us an opportunity to actually relatively easily carry out a attribution exercise by doing simulations using step sizes that are varied or reduced in different components, either separately or in combination. So long story short, we did a pretty big set of simulations where we changed the various step sizes, and that set of simulations has provided us with a very useful insight into which model components are the key impactors in different cloud regimes. For example, thinking about low clouds, which have a big impact on the shortwave cloud radiative effect, we now know that the sensitivities that we saw earlier in the caused by all step sizes reduced together can be decomposed into the contributions from the shallow cumulus and the stratiform cloud macro and the microphysics parameterizations, basically club and MG2, which causes quite some sensitivities in the shallow cumulus and also sometimes even deep convection regimes. And then the deep convection parameterization and its interaction with other processes cause sensitivities in the trade queue regimes and also along the equator. And interestingly, for the stratocumulus, subtropical marine stratocumulus stacks, we found out that it is really the coupling between the cloud macro and the microphysics and the rest of the model that is having the biggest impact. And for high clouds, which have significant impacts on the long wave, on long wave, so the coupling between club and MG2 and the rest of the model now no longer have that big of an impact. Then we see that it's mostly club and the microphysics, the step sizes used by this part of the model, and also convection and its coupling with other processes that are having bigger impact. So that was our attribution, which gave us some first impressions of what is causing what sensitivities. And then in order to be able to reduce those sensitivities and increase the accuracy of time stepping, we will have to go beyond attribution and try to understand what exactly is the reason or are the reasons that cause these sensitivities from a numerical perspective and from a physical perspective, and then try to come up with hopefully revised numerical methods that address those root causes. So in this presentation, I want to talk a little bit about process coupling as an example. So here I'm showing again that plot of the influence of process coupling between the stratiform cloud and macro microphysics and then the rest model on the cloud radiative effect. And for us and for quite a while, it was really puzzling to see that this more frequent coupling would lead to a significant decrease of the cloud amount in those typical stratocumulus regimes. And it was also puzzling for us for quite a while to see this signal pretty strong in some of those regions, but not in some other regions. So I would provide our current understanding of the reason behind this. But before that, let me quickly mention a few pieces of background information and recapture some concepts for some of our colleagues here. So first of all, I want to mention that sequential splitting is the primary process coupling method used in the E3SM atmosphere model. So by sequential splitting, we mean, so imagining a two process equation or simple model that has, sorry, I need to adjust my monitor a little bit. So that has two processes, so A and B. And sequential splitting would mean that, okay, we deal with these two processes in isolation. First, let the process A operate and update the atmospheric state, and then hand that updated intermediate atmospheric state to process B, and let the other process do its work, and then finish the one time step in the time integration. And it can happen that the process B is known to have relatively short time scales, therefore need shorter time steps. And to save computing time, we might decide to subcycle the parameterization for process B. And if we still use the sequential splitting, we would pass that intermediate atmospheric state updated by process A to the first call of the process B process in the subcycle. Okay, so this sequential splitting has a potential issue, which is that it can cause really rather strong oscillation of atmospheric state within each time step if process A and B happen to be strong sources, a strong source and a strong sink that are compensating each other. So this is not only just in our conceptual understanding, but is really seen in the E3SM atmosphere model. For example, here I'm showing the time series of the global mean concentration of stratiform cloud liquid mass over 5 time steps, which consists of 30 subcycles for the cloud macro and micro physics parameterization. You can see that at the near the beginning of each time step, there is a huge jump of the cloud liquid content, and then followed by a few steps that have little ups and downs. So this some of our colleagues in the audience who have more experience with numerical methods might immediately realize that this can potentially cause large errors in our integration. And this kind of issue can relatively easily be addressed by taking small time steps for both A and B. But that can be time consuming if it happens to be a very expensive part of the code. And another relatively easy way to address that is that instead of doing sequential splitting, we can pass the atmospheric state that we had before A operated, and also the tendencies of the state variables caused by A, both to the subcycles, and then do the state do the state update within those subcycles. And indeed, if we implement such kind of a tighter coupling in our atmospheric model, we will see the blue time series in this figure, which clearly has a lot less oscillation. If our system is rather linear, or if the process rates are somehow constrained by other factors relatively strongly, then we might see more or less the same mean state before or after this change, and then you might think, okay, so maybe there is no big deal whether I have bigger or smaller oscillation. But unfortunately, our model is quite nonlinear, as the atmospheric processes are quite nonlinear at many places. And for example, in the subtropical stratocumulus regions, we realize that if we implement the tighter coupling, they, in addition to this reduction of the oscillation, we also see a systematic decrease of the cloud liquid content. And so on this slide, there is also a blue time, so green time series, which is from a simulation that uses a much shorter time step and no sub-stepping at all. So comparing those three lines, we can see that tighter coupling between the microphysics and the rest model does systematically push the solution towards what we think is more accurate numerically. But then still, there is the question: why is there this systematic decrease? So our understanding so far is that, so this has to do with the sequential splitting causing large oscillations in the model state within one time step. But now think about the fact that for marine stratocumulus, it's well known that near the cloud top, the long wave radiation typically cause a very strong cooling. If that, so assume that the same atmospheric state and also the same radiative cooling rate is passed, so is predicted, and then we only apply that change over a 5-minute time step, you would see a relatively small amount of cooling at cloud top, as indicated by this darker shading here. In contrast, if we assume this cooling will persist for 30 minutes, and then we would add a big increment of cooling effects to the model atmosphere. And so compared to the default model, when we use a shorter coupling frequency, we will have less cooling applied to the atmospheric state seen by CLUB. And based on our understanding of the turbulence parameterization and also the boundary layer physics, we will know that the weaker turbulence will lead to, the weaker cooling will lead to weaker turbulence, and then reduced cloud amount, which will again lead to weaker cooling and forming a positive feedback. And so we have looked at the E3SM global model simulations and seen that in those cases where we saw decreased stratocumulus, there was indeed the indication of weaker turbulence. And also we carried out simulations with the single column version of the E3SM atmosphere model for a typical stratocumulus case, which is by default configured with no shortwave radiation, and that case does not have deep convection, has no horizontal advection. And then we saw that with or without microphysics and with or without shortwave radiation, we always get qualitatively the same behavior, which is the reduction of the cloud amount. So and this gives us confidence that the cloud top, so the radiative, the cloud radiative, the feedback between cloud radiative, cloud top radiative cooling and then the cloud amount is a key factor in causing the sensitivities that we are seeing. I guess I'm a little bit running out of time, so I will skip the next two slides. But then simply say there was this puzzle why this signal is seen only in some places and in some seasons, but it turns out that our proposed hypothesis can very well explain this this phenomena. So that brings me to the conclusions of the work we have done on this topic. So we have seen that time step sensitivity is non-negligible in our atmospheric model. It's inconvenient for model developers who focus on model fidelity, and for us who are interested in reducing time integration error. This means that there is a lot of work for us to carry out. And going beyond the specifics of the stratocumulus and why it got reduced when time step is shortened, I want to say that since we have gone through this process of trying to quantify, attribute, and thoroughly understand the model behavior, we felt that we got more confidence that despite the fact that the model is very complex, one can still thoroughly understand the sensitivity and try to come up with revised time stepping schemes to address that. And the last slide, just to say, I only talked about process coupling, but we do have several pieces of work going on that are looking into the other sensitivities and their impactors, for example, deep convection, and also club and the microphysics. So that's all I have for today. Thank you.